Thank you, Elena, for a very nice presentation. And I'll try to share my screen in order to start. So let me see. I'm searching for the PowerPoint. Okay, that's it. Okay, you should now see my PowerPoint screen, and if so, I start. I don't see the chat window anymore, so if there are problems, please, Milena, tell me by voice. So here is my presentation slot. I will talk about the results coming from one project that is called AIRHERITAGE. AIRHERITAGE is a project funded by UIA. Then we will talk about the MONICA device, which is the low-cost multi-sensor system on which we will base our calibration. Then we will talk about the results of some calibration methodologies that we are using in order to take the most out of these sensors, and then some results of opportunistic PM measurement campaigns. And then we will talk about a little bit about the conclusion and the future works I envisage. So, AIRHERITAGE main goal is to raise awareness and for air quality in the cities, the small cities of Italy, and then to develop some participated remediation. Because one of the big problems is the distance that is between the regulatory agencies, the citizens, and the administration. So we filed this project to the 2019 Urban Innovation third call on air quality, and we were funded. It was really a challenge because it's a highly competitive call with less than 10% acceptance rates. So our main goal was to bridging the gap between the main urban administration, regulatory agency, and the citizens using a participated approach to monitoring and fact-based policy design. So it's a little bit a nightmare about communication in this project, because we have 5 channels of measurement and modeling and communicating air quality. Of course, we have the opportunistic air quality data and exposure data from more than 30 devices that are spread in the population. The population is using every day by moving inside the cities. We have continuous data coming from 7 fixed low-cost air quality measurement stations. We have predictive data coming from models. We have regulatory grade data coming from mobile stations and fixed stations too. So we have 5 different data channels with different accuracy, different space and time resolution, different targets and so on. It's a little bit a nightmare. We will focus today on the opportunistic data coming from low-cost measurement. Of course, we needed and we developed an IoT management system in which population can log in and understand the air quality trends in real time, and also understand the measurement that they have taken by moving inside the city with these low-cost monitoring systems. And you can see some snapshot coming from the website. So let's talk a little bit about the MONICA device before entering in the calibration realm. The MONICA device is a multi-sensor systems with equipped with 3 electrochemical sensors coming from AlphaSense that which have NO2, ozone, and carbon monoxide as target gases. We have the a plant tower PMS 7003 that is used for particulate matter concentration estimation, with a smartphone companion app with which the citizens can walk within the city and having real-time estimation of the air quality within its path. The architecture of this IoT management system is a little bit complex. You see that we have these two sources of information coming from low-cost systems. These measurements are calibrated and then assimilated within a model, forecasting model, that outputs air quality exposure index and the air quality index, and also, of course, a visualization. I have something in the chat, but I don't see what is the text. Sorry, it seems not to go. Okay, but let's go talking about the calibration in the field. So our goal was taking the most of the accuracy out of these multi-sensor systems, and in particular we will focus on low-cost particulate matter sensors that are in the multi-sensor systems. So these sensors readings are hampered by a lot of interference. I say the most important of which is relative humidity. We have a lot of literature in the past few years that are showing this, and I advise you to go in these two papers, from which you can discover other articles talking about this. And because the mechanism is really simple, so humidity caused the original vendor calibration assumption to fail because particles swollen, and this invalidates the measurement and the internal models, and worsening the accuracy figures. But also the composition of particles, of course, has strong influence on this original calibration from the vendor. And we have already some literature that's shown that field recalibration actually ameliorates the original calibration outcomes. So what we do inside the AIRHERITAGE project is that we do every 6 month calibration by co-location with a mobile regulatory grade station offered by the Regional Environmental Protection Agency. So this mobile station is located within the city, and we collocate those 30 devices on this track, and we record the data coming from the regulatory grade analyzer, which is something like 1 hour resolution, time resolution, and the 30 Monica device that output something like 10 samples so we average and we harmonize these time scale data sets, and we extract data for training some calibration algorithms that we will show in a few slides. First of all, let us check what are the performance of the original calibration coming from the vendor of these devices that I recall. They are the Plant Tower PMS 7003. So what we show here is that the original calibrations are two. One is called AA, that stands from atmospheric environment, and the other one is standard particles. And we see that basically one is better than the other, but the figures are a little bit poor, especially if we talk about R squared and RMCE. What we show here from the scatter plot is that there is some humidity effects. When you saw that the original calibration overestimates, and these overestimates are worsened when the temperature, the humidity goes above 70% of relative humidity. Basically, we can say that the Bayer sensors, the Bayer calibration consistently overestimates the PM 2.5, and the same apply to PM 10, and also sensitivity is overestimated by the original model, while the bias is really limited. You say it's more or less the average is about 1 microgram for cubic meter. So let's a little bit work another look at the scatter plot, and here it's more clear how the higher relative humidity has an worsen the overestimation effects. So what about PM10? PM10 is more or less the same. You can see that the humidity has the same effects, and also you see that the performance are really poor. So the R square factor is negative. So what we do? We start with a simple correction approach by relying on simple assumption on the nature of the error. So what we do is to correct the actual calibration, the pay outputs, by taking into account relative humidity and also temperature. So, so the function can be based on physical model assumption. What we do is to rely on data-driven approach, and basically we use multilinear regression, but you can also use physical model approaches. So this is the first approach that we do. So calibration by correction. We take the original estimation, we try to correct it, taking into account temperature and relative humidity. There are different approaches that we follow, we compare, but here what we obtain here is that multilinear regression outperform generalized multilinear regression and neural network approach, and actually ameliorate more than 30% some figures like the mean absolute error and the R square, RMCA, the centered RMCE, and the MAPE factor. So actually, we can obtain a huge boost in the accuracy just by using multilinear regression on a correction scheme. Of course, these results have been obtained by averaging time stratified sets, so there is no links between the training periods and the testing periods. We have used 2 weeks of training and 1 week test, and this performance has been averaged along all the 30 Monica devices. Of course, the same apply also significant boost in the performance just by correction. This is the outcome of what we obtained just to have a look at the scatter plots, and also you see that the interference coming from the relative humidity has been a little bit quenched to the low side. So we have partially solved this issue of the interference, and we have an effect of slight underestimation after a certain threshold that is about 40 micrograms per cubic meter. What we thought about is optimizing this performance by using additional features that the sensors actually provides to us. So these sensors actually provide particle counts in bins. These bins are 0.5, 1.0, 2.5, 5.0, and 10. All the particles of the sites that's below that sites are taking into account. And we wanted to take into account this information and understand if you can actually obtain a boost in performance by adding this kind of information coming from these sets. And actually, we found that this is true. Actually, we tested for a real performance boost, but we didn't obtain this performance that we thought about for PM 2.5. So more or less, the results are almost the same. And so we have no we tested for statistical significance of the difference that we observed, and there were no significant difference. So basically, by adding this information, additional information, we obtain no performance amelioration when regarding to PM 2.5. This fact is radically different for PM10 because we do obtain a significant amelioration of the performance. We tested for statistical significant difference, and we obtained a boost in the performance. So the lessons that we can take home from this slide is that field calibration actually ameliorate the performance, and also You can optimize this by adding all the information coming from the sensors, but this boost is only obtained, this latter boost is only obtained for PM10 estimations. Of course, the MLR shown to be the best in the breed for the models that we have compared. We showed result only of neural network generalized multilinear regression, and they are worse than the basic MLR. But another interesting model, the idea that we want to share with you is trying to get a scalable methodology for field calibration. Okay? Because the literature that we have produced is based on ad hoc calibration that are implemented for each and every census. And this is a little bit a problem when you scale up to tens of devices or hundreds of devices, like, for example, Milena is planning to do. Okay, so they are really costly. You need midterm access to regulatory grade station in relevant location. Location should be traffic to provide sufficient span. You need to perform field calibration for all devices. Okay, you really need all of this. Well, this depends on the census class that you are using, and in particular by the fabrication variants of the census. So how each census are different from any other in the batch. So what we try to do is to use global calibration approaches. So a global calibration process is the search for a standardized model that could be in principle used for all census, irrespective of the inherent fabrication variants. So we search for something that can be applied to all the census. So we can, in principle, select a subset of census, find the output by their particular vendor. Several approaches have been already provided in the literature for electronic music systems, the field artificial function from which I come from, but very limited efforts have been put at work for the low-cost air quality multi-census system, and in particular for the particulate matter census. So we have tried this approach, and we have tried to apply this approach to the correction method we shown a few slides ago. So one of the simplest, maybe too simplistic approach is to build a sufficient variance data set just by recording the response of a limited amount of correlated census nodes. We just take all the data, we put in the same data set, and we apply the same methodology that we have seen before. But our data set now is very much larger than before, because all the data the result by MLR in the correction framework like we seen before. So we're using the same data set as before. The global model has been released using randomly extracted 2/3, so 20 nodes, and testing on the remaining nodes. We have used 2 weeks of data and one for test purpose like we have seen before. And the performance of the test set that we will show are related with the other 1/3 of census, the remaining 10 census nodes that have been not calibrated, but we are using the calibration model that we have derived for the first 20 nodes. Okay, so these are the figures that we have seen before, and these are the comparison. Basically, it seems that for PM2.5, the global multilinear system actually outcome the ad hoc correction that we have performed for each and any of the 10 census we are using as testing. This is a little bit surprising, but of course there is a numerical effect in this because the number of the dimension of the data set is much larger for the global from the global model, and the variance of the census is very limited. So this favor this kind of approach. Okay, so but these preliminary results, basically what we are stating now is this demonstrate the feasibility of this approach. This is not true for, unfortunately, for PM10. Okay, the simplistic approach failed to provide on-par performance, but seems to come really, really close because we are in the limits of statistical significance at p equal to 0.05. So this basically means that you don't get better performance, but you are close to get on-par performance with a much more scalable approach. So most of the state-of-the-art scenarios now needs hundreds of sensor modes and frequent recalibration, okay, at least every 6 months. So in these scenarios, ad hoc calibration is simply not affordable. So global calibration will be a solution for this. Of course, use much more scalable methodology and lower the cost. But wait a little bit. This has been obtained just for one set of sensors. So we have randomly started 20 sensors, and then we tested on the remaining 10 sensors. But what about on the average? So we made a step further, and we averaged combinations of sensors for training and testing, because for example, we could be lucky to extract the best breed of 20 sensors for obtaining this global calibration model. So we averaged and we extracted just 6 devices, but this is random. This instruction is randomly repeated. Well, these are the output are shown in this slide, and we can see that the global R squared of the R squared of the global model actually outperformed. This is for PM 2.5, the average ad hoc R square. So the R square that on average has been obtained by the ad hoc calibration, like we have seen, correction, like we have seen before. So again, even by extracting and repeating this random extraction of different devices, you see that starting from 3 to 4 devices of involved devices, these are the devices, the number of devices that have been used for extracting the global calibration model. Just by using 3 devices, we are able to obtain a sufficient variance enough to cover the information needed to calibrate these 6 different sensors better and obtain better performance than the average ad hoc calibration. Okay, so here is the results obtained by increasing the number S of the device to 3 out of 5. So we have the majority of the sensors using for testing, and just the remaining sensors using for global calibration. And you see that by increasing the number of involved devices in the global calibration, again, we obtain better performance starting from using just 2 sensors. Okay, this is really exciting, interesting for me. This provides a mean to obtain a scalable methodology for calibrating hundreds of devices in principle. Okay, and similar results are obtained for PM10, but the best performance are obtained starting from using 5 involved devices, since that the variance of the sensors it's worse for PM10. And that's it. This is what is the lesson to take home from this slide. Well, it seems that global calibration models may provide a solution to the problem of the scalability of field calibration. Okay, of course there are other issues that are involved. For example, we know that the robustness of field calibration fade in time because of changing composition and changing environmental conditions, so we will work with a different approach. But this, at least for short period field operations, this may already offer a good solution. So of course these are preliminary results, but already with 30 different devices already provide a clue that maybe this approach really could be useful. And I will end my presentation showing what we do now with these systems. These systems are shared with the citizenship that may use them by collecting measurement around the city while they move for their usual business inside the city. So we have built opportunistic measurement campaigns, and we already have the result from one that have been run in June and July. You see some of the citizens that have participated with the Monica devices. They will be involved in 3 total campaigns in the duration of the project. At the moment, we have just one campaign that ended, another that is actually running now, and that will be another in the beginning of the next year. And the data that they share are used to build participative air quality exposure maps. We have seen that in the first campaign, we have actually used only 24 devices out of 30, but only 19 were active. We have obtained more than 1,000 monitoring sessions for a total of 1,937 kilometers, 10 hours of measurement, 59 sessions on average, and each of the people have monitored for more than 90 kilometers, more or less 16 hours. That means about 2 hours a week. That is an interesting pattern. So what we do is to make bins of 25 by 25 meters, and we collect data in this bin. If the bin has been covered by a minimum of 10 samples, we estimate the median, the concentration median, and the grid bins are colored according to the European Air Quality Index. That is a recommendation and communication index that is designed for near real-time interaction. So European Air Quality Index is shown to be an easy to understand communication tool, which have been accepted both by the administrative side and by the citizens as our way of communicating the results, and because this is an issue for communication. And we actually have shown the result to the population. Just to understand the European Air Quality Index error, so here you have a slide for NO2, and if you plot the grid of the relating to the different classes of air quality, you see that actually our measurement for NO2 makes some measurement by classifying the class just in these small corners that we have highlighted here. So for most of the time, 9 times out of 10 samples, the Monica device is capable to classify the actual correct European Air Quality Index class of pollution. And finally, let me show the biggest picture here. This is the picture that has been obtained, and these bins are 25 meters by 25 meters, and we have shown that there are some specific areas where accumulation of PM occurs. Some of them are nearby the railways, and some are nearby a very a crossroad with a very high traffic constantly during time, and these are somehow consistent with what we expected by the model. Okay, so let's close my presentation with the future work. So global calibration shows really interesting performance. It should be tuned and tested using all 3 field collocation campaigns. So this approach is very interesting because it may allow scalability for hundreds and more device deployments. Of course, we have to check for long-term robustness to seasonal variation. We can do with this data set that we are collecting, because every 6 months we have some collocation periods in which we can recalibrate, but also test the performance during the time. So we will also experiment with remote calibration strategies in order to correct for this. And also the last message is that the entire heritage dataset is open for collaboration, will be made also publicly available in the framework of the project wheels that we have together with Milena and Alena. And that's basically all for me, for my sides, and thank you for your attention. If there are questions, I will be happy to answer.
Thank you, Saverio. This was really nice. I appreciate very much this evaluation of how many units do you need for collocation. I have a short question for you. Have you done any evaluation of how people use it, or in which situations they use Monica, or what makes them motivated to use Monica? Because it seems to me that that is maybe the most difficult part of working with people, somehow making sure that they actually have a use for the technology and use it properly. Do you have any views on that?
Yes, we have some experience very fast in the first campaign, because we understood that those something was using it as a fixed station on the balcony, on their terrace, and they continuously outputting devices, measurement that this can skew the results, of course. And there are other people that were using, let's say, they mounted on their motorbike, and they were doing a lot of kilometers, because we set a price on the kilometers that they were actually measuring, okay, in the beginning, but we modifying this. And also there were people that were measuring just in the same place, because they want to show that that place was very polluted. Okay, so you have to you also have to in a way equalize, or at least provide in which you have a higher density of measurement. So this is really a problem, and I agree with you. But I feel really powerless on this, because this is not a matter of measurement. It's not a matter of techniques or technology. It's a matter of communication and involvement. And of course, I understand that I'm not particularly good at this. We have partners that are taking care of this, but people are really hard to work with. Okay, especially now in our country. I don't know in yours, and you made experience all over Europe, but we found our population really hard to work with. Especially if there is, for example, some conflicts with the urban administration, which was actually what we wanted to solve. Okay.
Thank you. Well, yeah, I think Nuria maybe will have also some insight on this. One last comment from me. I really find it extremely important that these experiences are somehow embedded in the metadata, in the description of the collected data. And I would like to highlight that these data will be part of the Vidis project, where we could play with them and find further how we can better use it. So over to you, Saverio, and Milena has a comment.
Yes, I have a comment. I met Saverio during the EUNETER cost action meeting, now to tell in person, but I think that he's pioneer of calibration of low-cost sensors. When I met him, I see that I read his articles about artificial nose calibration sensors before that, and he has one of the most experience in such a field, and we are in front of calibration in a field for project that we are going to run with UNICEF, that is Lydia Kesser now going to present, and I need to go precise in all that you explain us today, and try to adapt somehow. We have some exciting training in front of us because there is much more sensors that we need to use and to calibrate. So thank you very much for this very nice and useful presentation.
Thank you, and I look forward to have a look at the data and to work out a suitable methodology together with Milos for this project.